Hey everyone, welcome to The Explainer. Look, let's be totally real here for a second. Staring down a math paper from AQA, OCR, or Edexcel can be, well, pretty terrifying, right? You turn the page and boom, there's this massive, wordy problem about spinners or biased coins, and your mind just completely blanks. Trust me, I get it. But today, we're going to completely change that narrative. By the end of this explainer, I'm handing you an absolute game changer, an unbeatable probability toolkit. We're going to make those exact exam questions feel like an absolute breeze. So, think about it like this. If we treat your exam stress like an actual probability question, right now, your odds of acing it probably feel, like a pretty low fraction. But hey, I'm here as your expert tutor, and we're going to stack the deck in your favor. With just a few simple rules and some really neat visual tricks, probability actually becomes one of the most reliable, guaranteed ways to rack up marks on your exam. It really does. So here's our quick roadmap for today. We're hitting the basics of probability, then visualizing with sample spaces, and finally, relative and expected frequency. Let's get to it. Section 1, the basics of probability, building the foundation. Okay, let's dive right into this. Before we can start crunching the numbers and drawing out grids, we kind of have to decode the math jargon. Exams love, and I mean love, to throw very specific vocabulary at you. But if you know what these words actually mean, half the battle is literally already won. So first up is a trial. Probability is really all about just repeating actions and watching what happens, right? A trial is just one single repeat of an experiment where you can actually observe or record a result. Like, just one single flip of a coin or one roll of a dice. That's a trial. Which leads us straight to our next word, outcome. This connects perfectly to the trial we just mentioned. An outcome is, quite simply, a possible result of that trial. If your trial is flipping that coin, your possible outcomes are heads or tails. Snappy, straightforward, right? All right, moving on, we have an event. Now, an event is just a handy way to group those outcomes together. It could be just one single outcome or a whole collection of them. Oh, and exams usually label these with big capital letters, like Event A or Event B. Nailing down this concept is absolutely crucial because it sets up the whole foundation for the actual math formulas we're going to use in a minute. And finally, we have mutually exclusive. Now, two events are mutually exclusive if they absolutely, unequivocally cannot both happen at the exact same time. The classic analogy here is rolling a six-sided die. Getting a prime number and getting a 6, those are mutually exclusive events. You can't roll a 6 that is also magically a prime number. Unless you have some kind of rule-breaking trick die, they are mutually exclusive. It's just a really visual, intuitive way to think about possibilities that simply don't overlap. So bringing this all together, the absolutely crucial point is the number 1. This is the golden rule of basic probability. The probabilities of absolutely all possible outcomes of an event must perfectly add up to the number 1. 1 represents absolute 100% certainty. Seriously, if you remember nothing else from this explainer, remember that all your fractions or decimals or percentages for a complete set of outcomes, they literally must sum to exactly 1. Okay, lean in for a second because I want to share a little insider secret straight from the examiner's desk. Probabilities can only be written as fractions, decimals, or percentages, the whole shebang. Nothing else. Never, ever write them as a ratio. And here's the real high-value pro tip. If the exam question doesn't specifically tell you which format to use, fractions are normally your absolute best, safest bet. Why? Because they don't require any messy rounding, and they leave way less room for those silly little arithmetic errors that cost you marks. Let's see how all this builds into a classic, real-deal exam puzzle. Imagine Amelia's spinner. We've got 5 colors: blue, yellow, green, red, and purple. Now, we know yellow is 0.2, green is 0.1, and purple is 0.4. But blue and red are totally blank. The only clue they give us is that the spinner has an exact equal chance of landing on blue or red. So, how on earth do we figure out those missing values? Well, we bring in our golden rule. Step 1, we know the whole thing has to add up to 1, right? So we just take our known probabilities, that's 0.2, 0.1, and 0.4, and subtract them from 1. That leaves us with 0.3. Then, step 2, since the problem told us blue and red have an equal chance, we just split the difference. We literally just have that remaining 0.3. Half of 0.3 is 0.15. Boom! Puzzle solved. Blue and red are 0.15 each. Applying that one rule makes a seemingly tricky, stressful problem just incredibly simple. And you know what the examiner loves to do next? They might follow up by asking, what is the probability of the spinner not landing on yellow? Again, just use the rule of 1. If the probability of landing on yellow is 0.2, the probability of not landing on yellow is simply 1 minus 0.2, which leaves us with the highly satisfying final answer of 0.8. See how crazy easy it is when you just remember to subtract from 1? All right, moving right along, Section 2, Visualizing with Sample Spaces, the 2-dice hack. Let's add the next major tool to our kit. I'm going to show you a visual hack that takes those complicated, headache-inducing 2-dice questions and turns them into a super simple game of counting. Look, when an exam asks you to combine two things, like say rolling 2 6-sided dice, trying to list all 36 possible combinations in your head or even scribbling them on paper is a total recipe for disaster. You will almost certainly miss one. Instead, you need a sample space grid. Think of this grid as your ultimate structural cheat code. It neatly maps out the first dice on one axis and the second dice on the other. And here is where it gets good. Notice how the grid instantly does the heavy lifting for you. Let's say the question asks about the sum of the 2 dice. You just fill out the grid by adding the intercepting numbers. Do you notice those beautiful diagonal patterns popping up? Like all the 7s line up perfectly straight down the middle. Having this kind of structural organization completely protects you from making sloppy mistakes when you're under exam pressure. And here comes the real aha moment. Imagine the question asks for the probability that the sum of the numbers is an odd number greater than 5. You don't even need to do complex math anymore. You literally just look at your grid and play a fun little game of circling. We circle 7, 9, 11, 7, 9, 11, basically all the odd numbers greater than 5. And hey, notice, we did not circle the 5s because the question specifically said greater than 5. Gotta watch those details. Okay, once you've successfully circled your targets, you just count them all up. We circled exactly 12 options here. And how many total options are in the entire grid? Well, it's a 6x6 grid, so that gives us 36 total possibilities, meaning our probability is simply the number of successful outcomes over the total outcomes, 12 over 36. Now, sure, you can simplify that fraction down to 1 over 3, but the beautiful part is that the grid completely removed the stress of finding those initial numbers. All right, time for another insider tip. Examiners can be a little sneaky. Sometimes they'll try to trip you up by asking a 2-dice question without explicitly telling you to draw a sample space grid. Don't fall for it. Even if the prompt doesn't outright ask for one, preemptively draw this grid on your scratch paper anyway. It is honestly your absolute best defense against those complicated combination questions, for sure. Okay, last stop, Section 3, Relative and Expected Frequency. Math meets the real world. So what exactly happens when neat, perfect theoretical math collides with the unpredictable, messy real world? Well, we have to cleanly juxtapose two different ideas here. Theoretical probability is what absolutely should happen, like flipping a perfectly fair coin and expecting heads exactly half the time. But relative frequency, that's what actually happens when you run a real experiment. If you sit there and flip a coin 50 times and it lands on heads 40 times, well, you use relative frequency to estimate the real probability. It's basically how mathematicians test if a situation is genuinely fair, or if it's, a bit biased. Let's look at an actual real-world experiment. So Johan has this bag of buttons, and we have absolutely no idea what the theoretical probability is of picking a red one. So Johan decides to just test it out. He picks a button, puts it back, and repeats this 30 times. Those 30 picks are his total trials. Now, out of those 30 trials, he successfully pulls out a red button 18 times. So to estimate the probability, it's super simple. We just place those successful outcomes right over the total trials, 18 over 30. Before we wrap up, I want to give you one final examiner's secret, and I want this to act as a literal trigger warning in your brain. When you're sitting there reading an exam question, scan for the words bias, repeatedly, or experiment. If you spot any of those keywords, sirens should immediately go off in your head, telling you it's time to pull relative frequency right out of your toolkit. And there you have it. We've covered the fundamental rules, the sample space hacks, and exactly how to navigate real-world frequencies. You are completely equipped to break down any probability question they throw your way. But here's the real question I want to leave you with. How are you going to use this toolkit to calculate your own odds of success? Because mastering these concepts, it doesn't just help you pass exams. It literally trains your brain to decode the risks and rewards of the entire world around you. Pretty cool, right? Thanks for hanging out with me on this explainer, and I will see you next time.